Good morning to everybody and welcome in Galletti, even if this is just a virtual tour. My name is Michele Galletti. I'm managing director of the company. I represent also the third generation of the family. It's a a pleasure for me to see so many people interested in understanding and in discover our company. And I hope you will have 1 hour enjoying the facility and see what we are doing and listening from my colleagues all the history. Now I have leave the floor to Adam. Are you there, Adam?
I am here. Thank you. Thank
Okay.
you very much, Michele Galletti. Very good. So thank you, everybody, for joining us today and giving us your time. My name is Adam Hersh. I'm the Vice President of Galletti North America. And over the next hour, we want to talk to you about Galletti heat pump chillers. We're going to talk about hybrid heat pump, electric, gas-fired solutions. We're also going to take you on a really impressive tour of our R&D laboratory in Bologna, Italy. But before we get started, I want to say that over the past year, we've seen a lot of heat pump chiller manufacturers come into the market. The ones that have been here for a time, Aramec, Multistack. Then we had coming in over the past year and a half, 2 years, York, Train, and then some new guys, Quantec, Transom, Jetson. Most of these players had experience in chiller manufacturing, not so much in heat pump, or they're just new to this business. Over the next hour, we want to impress upon you that Galletti and its local representatives across North America are really the right partners for you. That at Galletti, we have 117 years of manufacturing comfort solutions, manufacturing out of Bologna, Italy, and exporting and having our equipment installed around the world. Our business is run by the fourth generation of the Galletti family. We are not a private equity-owned firm. We are not publicly traded. We are family run and operated. Through our representatives, we provide local field support, startup, and commissioning. I'm going to show a few slides just so that you can visually get a sense of what we've done here in North America and around the world. So I'm going to go ahead and share my screen. Okay, so this is our factory in Bologna, Italy, and you can see it's quite large. We actually have several factories in Bologna. This is the inside of the factory. You can see it's technologically advanced, and we have a heat pump equipment that rolls down the line each and every day, and again, exporting to our partners around the world. Our experience today isn't just with R32 and R454 refrigerant. We are also producing equipment that's utilizing R290 refrigerant, which is what got approved and is being exported around the rest of the world, and we expect here in North America within the next 2 years. The point I'm trying to make here is that we are not rolling out equipment with the 454B or R32 for the first time. We've been producing with these refrigerants for years. And by the time R290 gets approved here in the United States, we will have installations of this equipment tried and true and ready for air-free installations here in the United States. As a company, we don't just produce and export equipment. Our teams on staff include professional engineers that work hand in hand with consulting engineers to provide Revit and CAD drawings. We help get those drawings designed appropriately into the overall building drawings, taking into account our hydronic experience with plate and frame heat exchangers, pumps, air separation, storage tanks, and the like. With us, you're not just getting a manufacturer of equipment, you're getting 117 years of hydronic technical expertise, installing equipment that not only gets to the top of your building or outside your building appropriately, but is going to work for the long term. When the equipment gets produced, we have a laboratory, which we're going to be showing you a little later in this presentation. And from that laboratory, we test each piece of equipment, each machine, to make sure that it's going to produce the heat, the cooling, the domestic hot water as you expect once it's on your job site. In addition to the equipment, we also have accessories like the hydro kit, which you see circled on the top right-hand corner of this presentation. This equipment ensures that the water flowing in and out of our Galletti equipment is done with the right flow, the right pressure. Unlike boilers and water heaters, heat pumps are extremely sensitive to the flow of water. This is something that we've seen in our competitors' installations across the country where they have not worked as expected. So we take a holistic approach. We make sure that it's not just the equipment that gets installed correctly, but it's connected to the system as expected. So we take some ownership of that with you as our partner. In addition, on the left-hand side, you see a platform. We also provide prefabricated skid packages where we put the machines together and create a situation where they can be picked all at one time, whether it's a fully enclosed enclosure or a skid package, fully piped up as you see it. We provide that solution. These are just some pictures of some of our representatives' installations across the United States and Canada. This is in Boston with one of our fine representatives, FIA, which has over 50 years experience in hydronic heating, cooling, and domestic hot water. This is in downtown Boston and being used for heating and cooling applications, retrofitting chillers that were on the roof to be able to provide heating and cooling. This is our representative in the New York, New Jersey market, Wallace Ennis, with a domestic hot water application. And as you can see here in the picture, bottom right, the drawings that were produced for this job, the equipment, the Galletti equipment on the top, on the left side with the hydro kit pumping solution to make sure that that's done properly. And because it's a domestic hot water application, top right-hand corner is the storage tanks, plate frame heat exchangers, and what you can't see there are pumps and pumping packages. Now going all across the United States to Salt Lake City, Utah, another domestic hot water application for a multifamily housing application, and then an assisted living application in Vancouver, Canada. So whether it's the United States, Canada, Finland, Hungary, Germany, or anywhere else around the world, you can find quality Galletti heat pump chiller equipment installed worldwide, from grocery stores to 92-story towers. Galletti has the experience, the quality manufacturing, and the teams in the field to make sure that it's installed properly and running long term. So now I'm going to turn it over to Enrico, but before he takes ownership here, Bob Barrett is our senior sustainability director, and he will be talking about the hybrid solutions. And for some of you, it might be a little bit technical. However, I think it'll be very valuable to see the cost analysis of utilizing electric, gas, hybrid, as the applications are varied across the country, and then into our laboratory. So with that, I'm going to go ahead and turn it over to Enrico Monticelli in Bologna, Italy. Enrico?
Thank you very much, Adam. Good morning to everyone, and thank you so much for joining us today here in Galletti. So I want to just give you a very brief presentation to just underline some points that Adam already touched. One is that's very important to me is the fact that we are a 117 years old factory. We are no freshmen here, okay? We've been working in this industry for a very long period of time. We are located in Bologna, Italy. What we do here and what we have always been very good at is metal sheet processing. And in fact, a chiller, heat pump, a fan coil, everything that we manufacture is mostly made by metal sheets. So what we do inside is research and development, design, and manufacturing. What does manufacturing mean? It doesn't mean only manufacturing of a finished product. That means starting from a raw material, that's copper or galvanized steel in our case, we go to semi-finished products, up and down to the finished product. We try to do the most that we can inside our own factory, and we try to do it in a green way thanks to our solar cells. We do have a wide range of products and solutions here in Europe. Fan coils, chillers, heat pumps, and software and hardware for them. As you can see here, we are offering for North America a good range of air-cooled products, but here in Europe, we also do have water-cooled heat pumps and multifunctional air-cooled and water-cooled. And those are coming soon also for North America. This slide was shown by Adam as well, and this is very important for us because it shows we are really ahead and in technology, and we are ready to use the latest in refrigerant technology. So not only R410A, which is now absolutely the past, but we're going with R454B, which is the present, and we will be ready when the legislation will allow us to do so. We will be ready to use R290. Okay? We invest a lot in our production. We invest a lot in our facilities. It's very important for me to tell you that we've just finished a new R&D climatic chamber where we can test all of our units during the production phase, during the research and development phase, and also we can do factory acceptance tests there. We do manufacture units for the US with hot water production up to 149 Fahrenheit at 12 Fahrenheit ambient. And that's what we actually tested in our chamber. We tested those units exactly in those conditions. So we are pretty sure that they will actually work in real life because it's not just a catalog statement. And we also, of course, be able to produce hot water production up to 139 Fahrenheit at -4 Fahrenheit ambient. And we tested this point as well. Okay, so thank you very much. I'm now leaving the floor to Bob, as Adam said before. Bob is our Director of Building Systems here in Galletti North America. No, okay. Before that, we have a video that we can show you. Okay, thank you so much.
There is a place in Italy where technology, creativity, and passion have always reached their peak, where culture, art, technology have coexisted for centuries, where industrial design and engineering excellence culminate into peak performance. Bologna, Italy, where the oldest university in the Western world is located, where engineering minds have been shaped for over 900 years, where entrepreneurs and engineers come together, resulting in a mechanical manufacturing hub known for excellence throughout the world. Bologna, Italy, birthplace of some of the world's most iconic automotive and motorcycle brands. Galletti is a local family who founded a business in 1906 to produce products that would encompass excellence in design, functionality, and operational excellence. Today, the Galletti family has grown into a worldwide brand that manufactures ultra-efficient commercial heat pump chillers for heating, cooling, and domestic hot water. Galletti, a company that is proudly owned and operated by the Galletti family. A company that invests in future-oriented solutions. An advanced design company focusing on research and development, design and production through an innovative approach. Today, we are highly focused on low GWP solutions, designing and manufacturing heat pumps that perform at peak efficiencies while also reducing carbon output, that utilize sustainable refrigerants for today and tomorrow. In the North American market, we have introduced heat pumps with R454B refrigerant, while at the same time, we are shipping units with R290 refrigerant to European countries. In North America, Galletti has partners with HVAC Specialty, a company with over 100 years of applied hydronic HVAC and domestic hot water experience. A company that works with the largest network of manufacturers' representatives and wholesale distributors to bring the Galletti brand to market stocked and supported locally. From design to startup and after-sales support, our network is available in every North American state and territory. Together, we can make the difference. Together, we win.
Very good. Thank you very much. So now it's Bob's moment. Bob is the Director of Building Systems in Galletti North America. Good morning, Bob.
Morning. Can you see the presentation?
Yes.
Good. Okay. Let's try to move this over here. All right, very
Speak
good.
up a little bit, Bob.
What's that?
Speak up a little bit. Your voice just got a little bit softer.
Interesting. Okay. Hopefully this is good. Can you hear me now?
Yes.
All right. So we're going to talk about electrification made practical. This is a presentation that talks about a hybrid approach to electrifying HVAC and plumbing systems. So there's a major push globally to utilize electric power, HVAC, and domestic water equipment to decarbonize the built environment. Heat pumps can operate adequately in low ambient conditions in most of North America, but they do so at lower COPs in the winter months and with higher operating and first cost. We're going to talk here a little bit about how our power is made, because I think it's a good basis to kind of understand the whole electrification thing. So most of the power that we get is made by steam turbines. So we take water, we boil it up to very high pressures, temperatures, run it through a steam turbine. The fuel for that, generally speaking, is fossil fuels. And there's a thing called heat rate, which is the measure of thermal energy that's put into a plant to get a certain amount of electrical energy. Most gas-fired, steam-driven power plants work with a 33% heat rate. Now, if you use a combined cycle plant, which basically uses a gas-fired generator, that you're basically burning gas at very high temperatures and pressures, which spins the turbine, and then you take the waste heat from that and use that to generate steam as well, you can get that heat rate up to 45%. Still, it's a fair amount of the input energy that's essentially being wasted through heat to the atmosphere. Now, if we look at different types of steam generators, mostly it's either, some sort of fuel, could be coal, could be something else, oil, natural gas, but nuclear, right? And with nuclear, we're generating steam essentially. And with all those steam generations, you're running about 33% heat rate. Gas turbines, a little lower, about 29%. Internal combustion engines, we're 33.5%. And then that combined cycle, as we mentioned before, would be about 45%. Now off to the right here, these are their different forms of power. So of all the steam generations, right, we got our fuel sources, be it, fossil fuels or nuclear, whatever. We also have hydro plants, wind, solar, concentrated solar, and tidal power, geothermal to some extent. And all those other technologies there are greener technologies, right? They don't rely on fossil fuels. They don't emit carbon into the atmosphere. So if we look at the US grid, on average, it relies on fossil fuels for roughly 57% of the power generation. The remaining bit is 17.3% nuclear, 5.6% hydropower, little over 10 with wind. Solar is about 8. Geothermal is a tiny little fraction. Biofuels are 1%. Coal still pretty significant, 16%, and gas is the majority of it, right? 40%. So what we want to do here is take that concept of a heat rate, but then apply it to the grid. And we want to look at it in terms of what percentage is fossil fuel based. And, we might be running at between 33 and 45% with transmission losses and whatever, we'll round it off to about 30% heat rate effective. And then if we look at the remaining 43%, and we basically say, look, that's all green energy essentially. So we'll make that a heat rate of 1 as far as the carbon output goes, essentially. We end up with like a revised effective heat rate of about 60% for the US grid. Now, if that got to 100%, it would basically indicate 100% green energy. All right, so let's take a look at Washington State. So Washington State has a lot of hydro, and they have some other green energy that they throw in the mix, but mostly hydro. And it relies on fossil fuels for quite a bit less, only 19%. So if we look at the effective heat rate there of the grid, so to speak, in Washington, it's about 86.7%. So the whole idea of electrification is that today, right, there's some advantages to electrifying, but as the grid gets greener and greener, those advantages are going to increase. Now let's step back here for a second and talk about the point of use efficiency of an electric heater. So we already talked about the effective heat rate of the grid. Let's assume that's about 40% on average with a gas-fired system. So transmission losses are roughly 10%. So that gives us an overall efficiency of, let's say, 30%. Now, an electric water heater, or boiler for that matter, is 100% efficient at providing thermal energy, because any sort of wasted energy takes the form of heat, and you're heating, there's an immersion element that you're trying to heat. But when we take a look at the point of use efficiency, it's quite a bit less, right? So if we're talking about a gas-fired power plant, really we're looking at about a 30% efficiency from the point of where the fuel's going in, off of that 100% efficient electric water heater. Now, this is assuming, of course, 100% fossil fuel-based power, which our grid isn't. Now, if we take a look at the point of use efficiency in the US on average, right, which had that effective heat rate of 61%, what you can compare that to, if we're burning gas at a power plant and we're getting 30%, or we have this combined, grid that's got a greener efficiency. If we compare that to just burning gas on site with a condensing gas-fired equipment, and let's say it's running at 90% efficiency, the question is, what would the COP need to be as efficient on parity with that condensing gas-fired piece of equipment? And the answer is, in the US market as a whole, it would need to be about 1.5. Now, if we take a look at Washington State, which has got a much greener grid, the COP only needs to be 1.05. Now, the COP of an electric heater is 1. So in Washington, because the grid is so green, electric resistance heat is almost on parity with a condensing gas-fired piece of equipment. Not quite there, but it's a very easy bar for a heat pump to hit. And in fact, even in the US, across the nation, it's a pretty easy bar for a heat pump to hit. Now, this is an oversimplification because the US really consists of 3 basic huge grids. There's one that's sort of the Midwest all the way to the East Coast. There's the West Coast, and then Texas has its own grid. So the actual fuel mix is a bit more complicated. It's quite dependent on weather and other things as well. So this is simplistic, but it gives you the idea of sort of where the grid is trying to go. So the question is electrification green? Does it lead to less carbon emissions? So if you're in Washington State, yeah, extremely green, right? As we mentioned. Washington State requires limited carbon production and it has mild winters. So the average COP in the winter is closer to 4.0 and it only needs to be 1.05 to beat the most efficient gas-fired pieces of equipment. Even pure electric resistancy is on par with gas-fired equipment in Washington. If you look at the US as a whole, right, it's still very favorable. All right, so I'm kind of repeating myself here. We'll continue. So weather data, this is New York City bin data, and this is zones 4 and 5. So if you look at zones 4 and 5, 5 is in the green here, 4 is in the yellow. And you can see that cuts right through New York City, but it also cuts through a lot of the larger population areas of the US. So it's a pretty good sort of barometer for most of the country. Now, we design our systems in cooling mode and in heating mode for these extreme cold temperatures. And what you can see here, this is the hours of operation within these bin temperatures. We spend very little hours here. By design, it's less than 1%. So 99% of the time, we're in less extreme environments. And we spend the majority of the time in this range here, which is extremely favorable to heat pump operation. So there's a couple of things we need to think about when we talk about heat pumps and comparing it to gas. There's this concept of a spark gap. You hear it a lot when you're talking to cogen guys, but basically it's the ratio of electrical cost to fossil fuel cost for the same unit of energy. So the bigger the gap, the more cost-effective fossil fuel energy tends to be. Due to high spark gaps, gas-fired equipment costs less to operate in most regions of the US compared to electrical equipment. Gas-fired equipment costs significantly less to purchase currently compared to air source heat pumps. They'll probably always remain that way just because air source heat pumps are more complicated to build than gas-fired equipment is. So if first costs and energy costs were the only factors at play, few customers would choose to electrify at the current moment. That said, in some areas of the country, it makes sense to electrify right now, but we're going to talk about that comparison here in a bit. Now, the problem is the price of fossil fuel does not capture the external cost of using fossil fuels. So electric mandates and carbon taxes are being used as an incentive to change market dynamics. Climate goals are based on reducing carbon emissions, not on first cost. From a carbon perspective, heat pumps are better for the environment compared to direct fossil fuel equipment. With electrification mandates and carbon taxes having an impact, heat pumps are becoming a requirement. The question is there a way to hit the carbon goals while keeping cost reasonable? So we're going to do a comparison here. This is a condensing gas-fired piece of equipment, and our design conditions in this case are going to be 5 degrees ambient. We're going to have 140-degree leaving water temperature with 125 return water temperature. Now, on a design day, our condensing gas-fired equipment is not going to be full condensing, so it's going to have a 90% efficiency. But as a seasonal average using leaving water reset, we can get to 94% with this particular application. Now we'll compare that to a Galletti air source chiller heater with the same conditions for design for the leaving water and for the ambient air. On a design day, when it's 5 degrees ambient outside, the COP is 1.75. Now that's 75% better than an electric resistance heater. And if you're talking about it from an efficiency standpoint, it's essentially 175% efficient. And you might be thinking, how is that possible? With heat pumps, most of the energy is not coming from the compressor, it's coming from the outside, and you're basically getting free energy from the outside. So we look at the efficiency as the electrical energy we're paying for versus the thermal energy we're getting out. And with a heat pump, you end up getting a lot more energy out of it because of the free energy from the atmosphere than the energy you're inputting electrically. Now the COP over the season is 3.5 in this example. So if we take a look at that, right, we have our US grid, which is roughly a quasi heat rate of 60%. If we take that 60%, multiply it by 1.75, we end up with a point of use efficiency of 1.05, meaning that if we're burning, whatever fuels we're using for the US grid as a total, we're still above what a condensing boiler would be, which would be around 90%, right? So we're about 15 percentage points better. So you're burning 15% less carbon in the air, essentially. But that's not the whole story. If you look at it as a seasonal average, which is maybe more useful, it's a point of use efficiency of 2.1. So it's basically twice as good or consuming half as much carbon as a fossil fuel-based piece of equipment, right? So 2x is, definitely worth thinking about and noting. And obviously, as the grid gets greener, that same piece of equipment will become less carbon emitting because the grid itself will get greener, right? So it makes sense today from a carbon perspective. It's going to make even more sense in the future as the grid gets greener. So we'll work through some math here. So this particular plant, we'll say we're 3,000 MBH or 3 million BTUs. As a mean seasonal average, 30% of the full load tends to be what the mean seasonal load is. So we end up with around 900 MBH. This plant's going to run 24/7, 222 days. So that gives us about 5,280 hours of operation during the heating season per year. It's a pretty big number as far as BTUs per year. We can convert that to therms. We end up with 47,520 therms. And we can also convert this over to just pure kW. So that's 1.3 million, 1.4 million really, kW of electric heat per year. Now let's take a look at this. If we had a 100% efficient gas-fired piece of equipment and it cost us $1.40 a therm, which is, I got these electrical rates. We're going to do the comparison in Seattle for this one. Pretty good for a Seattle rate, 140 a therm blended. It's about 66,500 for the year. Now that's 100% efficiency, which is not reality. So we're going to get to the efficiency in a moment there. Now, when it comes to the electrical cost, in this market, it's 14 cents per kilowatt hour. That's a pretty big number, right? It's almost $200,000. And that, gives us a spark gap of essentially 3 to 1, more or less. If we take a look at the efficiency, now we said seasonally we were operating about 94% with that gas-fired piece of equipment. We end up with an annual cost of $70,000. Well, if we have a COP seasonally of 3.5, then the utility cost in Seattle for this heat pump is $55,000. So today, with the current grid in Seattle and their current electrical pricing, it's cheaper to run an air source heat pump than it is to run a gas-fired piece of equipment. Now, in Seattle, the spark gap's roughly 3 to 1, meaning that the gas costs 1/3 of the cost of electricity. So gas is still quite a bit cheaper. But an air source heat pump plant with a seasonal efficiency over 3 results in lower operating costs. In this case, we have a COP of 3.5 seasonally. So we end up saving money compared to the money we would spend with a gas-fired plant. And it's that free energy, right, that we're extracting from the environment that basically allows us to counteract that spark gap, that additional fuel cost for electricity versus what gas would normally cost. Now, in different markets, when you run through these numbers, right, it's not always favorable to air source heat pumps. So you got to look at your local market and kind of figure things out. But just to know, today, air source heat pumps do make economical sense with existing utility rates in certain markets. Now, heat pumps derate below freezing, causing plants to increase. Now, if you're designing for 5 degrees or 0 degrees, you can, basically what'll end up happening is you'll have to compensate for that derate if you're doing a 100% air source heat pump plant, and you'll end up with up to 30% additional capacity that you're only going to use a few bin hours a year. If you utilize hybrid plants, which is a mix of gas-fired units and air source heat pumps, then you can offset 80% of the carbon while keeping your first cost reasonable. So we're going to take a look at this comparison. We're going to look at a 3 million BTU plant, and we're going to do sort of a typical N+1 redundancy. So we're going to have 3 1,500 MBH boilers. So 2 of them operate at peak condition with a third N+1 kind of remaining off and waiting to be called on. And we're going to compare that to 7 nominal 750 MBH air source heat pumps, but they derate down to 500 MBH at 5 degrees ambient. So we need 6 of them to hit our capacity, and we have a 7th for N+1 redundancy. Now, the nominal cost for a condensing gas-fired piece of equipment is roughly $36 per 1,000 MBH. So we have a total installed capacity of 4,500 MBH. So it results in $162,000 of equipment costs, just equipment only, not gas lines, not flues, not all the other stuff, just the equipment. Now, if we look at the nominal cost for an air source heat pump, it's roughly $259 per 1,000 MVH. So here we're looking at $1.3 million, quite a significant increase in first cost. Now, just kind of, we don't have to hold those numbers. We're going to put them up top here again, so you don't have to memorize them. We're going to look at a hybrid plant, but this time we're going to say, hey, look, we're going to design our heat pump to give us full capacity down to 32 degrees or thereabouts, and then we'll have the gas-fired heat pump, which will take over below that temperature. So here we've got two 1,500 MVH gas-fired boilers, so they're essentially there. They can hit the full peak capacity without any input from the air source heat pump when it's extremely cold. That said, the air source heat pump will continue running and providing heat down to extreme colds. We're going to size our heat pump for this capacity, so we're not going to derate it quite as much. So our nominal 750 MVH units only derate to 650 in this case. We're only going to go with 2 of them. So with 2 of them, that gives us quite a bit of capacity. It's roughly 1,500 MVH, a little bit less at those colder temperatures. But basically, that gets us 70% of the year worth of operation, plus or minus a bit. And so by doing that, we lower our first cost to $389,000 here. We're at $108 over on this side. And so we end up with a total plant cost for a hybrid plant of just under $500,000. So the bad news here is the hybrid plant is still 3 times more expensive than a traditional gas-fired plant, but it's 36.5% the cost of a fully electrified plant, basically just no gas, right? So that's a huge savings. And at the end of the day, we're still covering 70 to 80% of the carbon emissions that we would if we had a fully electrified plant. So you're getting a huge first cost advantage with not that significant of a ecological disadvantage. Some more good news. Energy incentives can reduce or eliminate this first cost disadvantage. There are pretty generous incentives currently for heat pumps around the nation, and oftentimes that will pay for the equipment and even some of the installation. The other good news is the COP advantages can offset the spark gap disadvantages, leading to perpetual utility savings. As noted previous slide, in Seattle, there's currently a utility benefit to going with heat pumps outside of the carbon benefit, or even the incentives on the first cost. So there are things to consider when we're talking about electrification versus using gas. So one is, if we're talking new construction, if you have a gas piece of equipment, you need mechanical room for that gas piece of equipment. You need to run category 4 flue vents. You need to pipe it out with gas. You need to provide gas service to the building. Obviously, on the electrical side, if you're going to go full electric, there's some electrical upgrades that have to happen there too, or just additional electric that you wouldn't need with gas. If we're looking at retrofits, the gas infrastructure is already there, so the comparison kind of favors gas typically, but you might have to reline your chimney, and depending how big the chimney is, that can be quite expensive. The electrical upgrades obviously are another consideration as well. If we're talking about recurring expenses, utility costs are certainly a concern, so you have to look at that for your individual market. And then maintenance costs as well, they vary with these 2 different pieces of equipment. Gas-fired equipment probably needs more regular maintenance, but it's cheaper along the way, essentially. Heat pump equipment needs a lot less maintenance, but when it does need maintenance, it tends to be more expensive. So they probably even out over time, but it's a different sort of flow of maintenance cost. Incentives and penalties. So currently there are carbon taxes in places like New York and other places around the world. And then there are green initiative rebates that don't exist for gas-fired equipment. And then, of course, you've got federal, state, and utility rebates as well. I'm just showing the ones in New York, but they exist throughout the entire country. So one thing we didn't mention until now is refrigerants. So I want to talk about how important is the GWP. This has been a big topic, right? Everyone wants the lowest GWP possible. So let's take our 30-ton unit. It's 30 tons, it's roughly 62 pounds of refrigerant. It's got a GWP, the R454B refrigerant has a GWP of 466 pounds. So what that means is for every 1 pound of refrigerant is equivalent to 466 pounds of carbon dioxide being released into the environment. So carbon dioxide is sort of like the baseline number. Now, this has a total equivalent CO2 of 20,000 pounds, which is roughly 14 tons of carbon dioxide equivalent. So if you were to release the entire charge, that's how much carbon dioxide equivalent you'd be releasing into the atmosphere. Now, something to think about is that refrigerant pieces of equipment are hermetically sealed. So you charge it with refrigerant. It's not like you're just blowing this out constantly. It stays in the equipment. And it stays in the equipment for the life of the equipment. Now, normally equipment, when it dies, right, it leaks refrigerant. That's one of the reasons that it dies. So usually it eventually escapes. But let's take a look at that contextually. So Local Law 97 in New York gives us some factors for the amount of carbon dioxide if you're taking electricity off the grid, because our grid is not purely green. And then it gives you the gas equivalent for MBH of tons of carbon dioxide. So if we take a look at the plant energy per year, assuming a mean seasonal load of 30%, 5,800 hours of heating with a leaving water temperature of 140, we end up with roughly 140,000 kilowatts per year. And so if we take the electrical component of this and we multiply it out, we end up with 40 tons of carbon dioxide equivalent. That's running our air source heat pump plant in New York City, basically. Now, the impact of a release of the charge would be 53% of 1 year's heat pump operation. So roughly half of the year's just normal power off the grid carbon emissions would be the equivalent of that release. If we're talking a condensing gas-fired boiler, it's only 35% of that. Now let's talk about this for a second. So if the air source heat pump operates 25 years without losing its charge, if and when it did lose its charge, it'd be equivalent to basically 2.5% of the carbon impact of that plant over the course of its lifetime, or 1.5% if you're talking comparing it to gas-fired equipment. So while 466 might seem like this big number, when you look at it in context of the impact of losing that charge in terms of global warming, it's not as significant as people assume it is. And that is also why heat pumps are being utilized, because while it's not perfect, it's still a lot better than burning gas continuously and emitting carbon dioxide, which is a global warming gas. All right. So let's talk about schematics a little bit. So if you want to implement a air source heat pump, right, you can do it kind of the same way you would with a boiler with a primary secondary connection and just pull from the loop, inject heat. If you want to have a gas-fired boiler and an air source heat pump work together, it's a pretty easy thing to do. What you do is you sort of nest the primary secondary taps so that the two cooler returns still go on the return side to the air source heat pump and to the boiler. And then the injection, you have the heat pump inject prior to the boiler. Now, typically, the heat pumps are going to run off of return temperature because it's a slow reacting signal, leads to less cycling. Boilers tend to react to the supply water temperature sensor, so usually that's going to be downstream. And so you can either set the set points farther enough apart where there's a gap where the air source heat pump is always sort of stage 1 and stage 2, or you can have a third-party controller that basically turns on air source heat pump 1 and 2 as stage 1 and stage 2, and then turns on boilers 1, 2, and 3 as 3, 4, and 5 stages, essentially. So reasonably simple means of integration between those two. If we're talking domestic water, what you want to do is have the heat pump heat up the cold water and the recirc from the system. And then if it's keeping up with the load, basically hot water leaves this tank. It goes into the cold water port of the storage tank. And then this is just extra storage. Now, if it can't keep up for some reason, then the gas-fired plant would come on. So the gas-fired plant is very much secondary, and the goal is for it to never come on. But if it has to come on, it's there to back up the system. Now with this, there's no need to controls integrate anything. It just sort of happens. Water goes into the air source heat pump indirect tank first, flows out of that into the secondary tank, which the gas-fired system is referencing. Now, if you have a lot of air source heat pumps, one thing we tend to favor doing is using a 4-pipe buffer tank for that, especially for domestic water applications. The benefit of doing this is a few things. One is it decouples the flow rate on the air source heat pump side with the indirect side. So you can have, a 10-degree delta T over here. You can have a 30 or 40-degree delta T over here. You can size these pumps for much smaller flow rates, much smaller piping, smaller heat exchangers, smaller electrical demand. And then also from a control standpoint, The air source heat pump is just looking at the middle of this tank, which is a slow reaction, and it can charge hot water on the way down. It can store cold water on the way up, so it delays the response of the air source heat pump. And then it just sequences these on as required by the slope of that temperature. Over here, these can have their own individual aquastats. They turn on both of these pumps when there's a call for heat in the tank, and then they shut off when there isn't. And so you've decoupled controls, you've decoupled flow. It's a very simple system, very easy to maintain, doesn't require a lot of sophistication. Now, in the beginning of the presentation, Adam showed our hydro kit. It was sort of like Gen 1 hydro kit, kind of came off perpendicular. Our Gen 2 hydro kit's quite a bit more compact. So we did something pretty basic, which was put an elbow on it. And doing that allowed us to get much more compact with that hydro kit. You can see our units very easily serviceable. This CAD drawing is a little weird. This piece of metal doesn't exist. It actually is a V-shaped piece of metal, so air flows in on the ends here. We can build this with a 2-pipe configuration, or we can build it with a 4-pipe configuration. Now, this is still essentially a 2-pipe unit in the sense that these modules are either heating or cooling, but we can have, in swing months, 3 of these in cooling, 2 of these in heating, vice versa, or any kind of combination thereof. Our hydro kit's very easily accessible and serviceable, and we provide it with isolation valves, pumps, Y strainers, and check valves. So we have this sort of with and without a pump option. We have it 2-pipe or 4-pipe. Now, as far as spacing goes, we will go as close as 6 inches between the modules. The reason we do that is the closer you get, the more difficult it is to kind of service things. But if you give yourself some spacing between the modules, if you ever had some sort of catastrophic issue with the unit, you can rig it out of place. Now, a lot of our competitors have everything just slammed together, which makes it much more difficult to service. Even the way that they do their piping is very difficult to service. And so we are designing with serviceability in mind, but also trying to keep things as compact as possible. Another thing you'll note too is, and I guess I showed it on another slide, I don't necessarily want to go back, but
Hey, Bob, I'm sorry. Bob, I just want to cut in here a second. And it hasn't been announced to you yet, but we do have the 0 clearance models now available. So we can do 0 clearance on these. And also, as you see the frame underneath the units, again, that is a prefabricated skid system with the headers built on. So we can work with you to apply these as individual units that get installed and picked up by the crane one by one, or they can come prefabricated on a skid with the piping and the hydro kits and pumping all involved. Bob, if you wouldn't mind, I would want to make sure that you talk about the Abbott effect that we discussed yesterday. Thank you.
Sure. So, yeah, what Adam's discussing there is we've been in the hydronic business for a long time, and there are a couple of principles with hydronics that you kind of want to maintain. So one of them is primary secondary pumping is something that has been around for a very long time, and we highly encourage it. When you have an air source chiller heater, you want to make sure that the air source element is controlling the pump that it's going to in the flow rate. So we've sized this appropriately for flows, and when the thing comes on, it comes on a little bit ahead of the unit, gets the flow going. When it shuts off, it keeps water flowing for a while, and it makes sure it carries away all of the energy. When you shut off a gas piece of equipment, there's a little bit of heat in that heat exchanger, but when you shut off a unit that's in cooling mode, refrigerant is boiling, and you need to carry that heat away. And if you shut it off and you don't control it right, or if you're at too low of a flow, you can freeze the barrel, right? So it's critical that you control flow right. So not only are we doing that, but we also highly recommend reverse return with all of the assemblies. Doing that allows for appropriate flow. Now, I've actually done flow studies and seen situations where with direct return situations, like the first 2 in line will flow fine, and then you turn on the 3rd or the 4th one, and the first 2 kind of deadhead the 3rd and 4th one. it's counterintuitive. You think, it's all roughly the same head loss. But when the head losses are really close, you're on the suction side of the pump, you can get some really wonky hydronics. If you do reverse return, it makes that go away. Now, a lot of our competitors have hydro kits that don't have balancing valves. They don't have check valves, rather. They don't have strainers. They don't have pumps. And so what ends up happening is, and they do direct return. And so they're having flow issues. And we're hearing reports of compressor failures. And, if you get a bad failure, like you freeze the barrel, water and refrigerant mix, you might as well just throw away your unit. So we are trying to protect our clients by doing the right thing with the hydronics, and we're seeing a lot of expensive lessons out in the field from our competitors. Let's put it that way. So, all right. So let's wrap this thing up. So conclusions. So first, cost-wise, hybrid plants provide 80% of the carbon reduction of full electrification at half the cost of a fully electrified plant. Caveats here: energy incentives and carbon taxes can significantly change that analysis. So, it's oftentimes we're finding that fully electrified plants are less expensive if we're talking new construction. If we're talking retrofit, little trickier to make retrofits work financially, but we can make it do it with incentives. Operating cost comparison: 100% plants using air source heat pumps can cost less to operate in areas with low spark gaps, but they can be more expensive in areas with high spark gaps, so you have to do that analysis. Ecological comparison: air source heat pumps have a lower carbon emission by a factor of 2 to 4x. So even with today's grid, it still makes sense to go fully electric if you're concerned about that. Hybrid plants are a good approach to balancing climate concerns and economic concerns. In terms of resiliency, gas-fired equipment requires significantly less power to operate, which makes backup systems more cost-effective and feasible. So if you have a critical system that can't go down and you don't want to have a power plant for your fully electrified system, having some gas available can help you in those situations. Obviously, the gas distribution network is stable during extreme weather, so that can be a benefit as well. And at the end of the day, I want to leave with this idea, don't let the perfect be the enemy of the good. I think it's pretty clear that heat pumps are here to stay. They're a good technology. They make economic sense in many markets across the US, but even in the markets where the economics are a little trickier, you can still electrify for a good portion of the year and decarbonize and have an economic benefit along the way.
Thank you very much, Bob.
Yeah, and with that, we're going to hand it over to Mattea, who's going to provide us with a tour of the test facility at the factory.
Welcome, everybody. So for us, it's really an honor having you here. So thanks a lot for your presence and your time, too. My name is Mattia, and I've been working in Galletti for 10 years now, more or less. I'm a product manager for chillers and heat pumps, and I follow the growth of 88 range with R410A and the future step, so with R454B2. Next to me, Filippo.
Yes, I'm Filippo, project leader from technical department, and I've been part of Galletti family since 2018.
So thanks, Filippo. Now we have a 3-minute clip focused on the Galletti lab test. So due to the large number of people connected, maybe you could have some problems, but don't worry, okay, about that, because for sure we can share the clip in a second time, but more important, we come back in 3 minutes here, okay? So, clip, please. Perfect, so welcome again. I try to translate, to convert some numbers, okay? So we are talking about a facility that allows testing the unit starting from -4 Fahrenheit degrees of air temperature up to 122 Fahrenheit degrees, okay? So a very wide operating range. We can handle and keep under control not only the temperature of air and of course of water, but also the humidity in order to have the more realistic operating condition. Because what we want to, from this climatic chamber is to have a realistic behavior of the unit, simulating what can happen on field. So not have just a nominal performances, but realistic performances. We can also, for example, testing the unit considering the defrosting cycle, okay, and also glycol system, because we have 6 water connections, that means 3 water loops, in order to test air-to-water chillers and heat pumps, water-to-water, so water condensate, chillers and heat pumps, and also multi-purpose unit with 3 different plate heat exchanger. So we can test each kind of units and also with glycol inside the water loop. Not only because, as you can imagine, the big volume of the room, okay, allows to have very low airflow speed, okay, in order to doesn't affect the performances of the unit with a very high speed airflow, okay? Just to consider that big units has very large airflow rate, and if we would test the unit in a very small volume, this would translate in a very high speed, okay, of air that can affect the performances, the realistic performances. And we can also test, of course, not only R410A units, but also R454B or propane units. That means the climatic chamber is already approved for testing low flammable and high flammable refrigerant and units. The result of this investment is that Galletti can present on the market very reliable product, okay, also considering the possibility to test in very realistic conditions all the units in advance before the installation on field. On my left, for example, we have a R454B units, okay, this is a VLS unit, something very similar to the ATH unit you will have soon in your market with R454B. We use a scroll compressor, okay, heavy ion scroll compressor that allows the production of hot water up to 146 Fahrenheit degrees. This unit has a cooling capacity more or less of 45 tons. We have a wide offer on this range because we can cover, this is the smallest model, we can cover a cooling capacity starting from 45 tons up to 180 tons, more or less, okay, so a very wide range. Consider that R454B ranges are available with the Galletti brand in European market since 4 or 5 years ago. So we have already hundreds, thousands of units installed on field, okay. So it's something that will be new, okay, for US market, of course, but it's something that we are already tested and make reliable in Europe. So this is our present solution and offer for European market, the solution of tomorrow for US market, but here we have also the future solution both for European and maybe, I hope, US market. So Filippo, tell us something about the propane units, please.
Yeah, sure. So as you may know, in Europe, we recently have the review of F-gas regulation, which basically stated that every refrigerant gas with GWP higher than 150 will be banned in a space of 3 to 6 years. So we thought about a possible solution, and we came up to the conclusion that propane will be the gas which is the most suitable, at least for Europe, for the future. And propane, it's a highly flammable refrigerant, but it has also some interesting potentials. So, for example, it has a low GWP, just 3, and it has also a low density and excellent thermodynamic performances. So, as you can see here, you can see one of the first prototype we worked with. This is a 16 tons unit, and it's obviously a propane unit. It's equipped with a variable flow compressor. And as you can see, the refrigerant circuit is very clean, very simple. We worked a lot on that because we wanted to basically reduce the number of braising points, which can eventually lead to, let's say, some refrigerant leakage. And we also used state-of-art refrigerant components, especially in the heat exchangers. And to put into perspective, in this unit, we have just 10 pounds of refrigerant, of propane. And if you have a look to something in R410A, for example, a refrigerant gas, you can easily find something that is in the ballpark of 20 to 25 pounds of refrigerant inside. And finally, inside the unit, we have actually the refrigerant leak detector, which basically stops the unit if there is any kind of leakage, and triggers the extraction fans, which basically flushes all the gas out of the unit far from any source of ignition. And finally, as I mentioned before, propane has a lot of potential. The most important for us is the thermodynamic potential that it has, because this unit is able to produce hot water, up to 176 degrees Fahrenheit, which is very high. And I think that is something that is never done before with an electric heat pump. So this opens also the doors to a number of projects, such, for example, boiler replacement, but also process heating solution. So back to Mattia.
Thanks, Filippo. Very interesting. So we have the third unit here, so we can walk in the climatic chamber just to take a look. Okay, this is a MLE unit available in European market, another time with R454B refrigerant. The most important advantage that this unit and this range offers is the total heat recovery. That means we can produce cold water, warm water, and also both together using the total heat recovery. That allows very great performances, okay, because during the total heat recovery mode, the unit automatically switches off all the fans, okay, because we don't need to exchange heat with air, okay, and just recover all the condensing power, enabling the hot exchanger, okay. We can also move behind the climatic chamber in order to have a look also on all the piping system. That is something very interesting, and also it's really the core, the heart of the system. Here, okay, we have all the tank, the huge tank we use for testing the unit. So the hot water tank, the cold water tank, the source water tank in case of water condensed unit. We have all the PEMS, the glycol loop, and so on. So, as you can understand, it was a huge investment for Galletti, but really it was and it is the only possible way to have advantage on the market related to an advanced design solution. So, for the moment, and thanks again for your participation, your time. I leave the floor to Adam if you want to add something. Thanks again.
Thank you, Mattia. Thank you very much. All right, everybody, I want to just thank you for your time. I believe that we have sufficiently demonstrated for you the quality of Galletti manufacturing, our engineering, understanding of not only the equipment, but how it interfaces with the hydronic system of the building, that we could help you with the hydronic heat pump plant design. We can provide in-field technical support in terms of startup and commissioning, and we would like to earn your business. We will follow up this presentation with an email out to everybody. We believe that we have sufficiently demonstrated to you a solution versus all the competitors out there to us, that we have the right product, the right people, the right solution for you. So I would say and ask the question, it does make sense to partner with a quality firm like Galletti, doesn't it? Turning it over to you, Michele Galletti.
Oh, thank you, Adam. Why? Oh, already is join us, Mattia. I would like to thank you very much for your time. It's been a really a pleasure to have you here, virtually, of course. But anyway, the next time we will invite you physically here, because it's better to see, to touch what we are talking about today. And from our side, is has been a good opportunity to meet again you, Adam, and Bob. And I hope that you enjoy the day. We are almost at the end of the day, so for us is we finished the day, so we are leaving now, and for you it's just starting.
Thank you. Right, it's time for aperitif at 6:30 in Bologna, Italy.
Yes.
So thank you
dinner,
so much for staying late tonight.
Or beer.
Thank you.
Yeah.
Thank you, everyone. Thank you for being with us today. Bye-bye.
Thank you.
Thank
Bye,
you.
Enrico. Bye, Mattia, Sylvia, and Michele Galletti. Thank you very much. Thank you, Bob.
Thank you.
Thank you, everybody, for giving us an hour. Oh, by the way, anybody who had questions that put into the chat,
Right.
We will follow up with answers to your questions via email. So we'll be shooting those out over the next day to you. Thank you for putting those questions in there, and we will be in touch with those answers along to talk about any project support you might have. Thank you very much, everybody. Sylvia, I saw you looking at me. All right. Thank you.
Thank you.
Thank you. Bye-bye.
Ciao.
Ciao. Bye.
Ciao, everybody. Bye-bye.